Example 3 is also asking us to use the given information to graph the function. Now, at first it tells us that the domain of our function is all x except for x equal -1 and x equal +1. So those are not part of the domain of our function. Then it gives us f of -2 is equal to 1, f of 0 is equal to 0, and f of 2 is equal to 1. Again, these are always just going to be ordered pairs. Then we're given information about our first derivative and then information about our second derivative. Finally, we're given that we have vertical asymptotes at -1 and +1, and that we have horizontal asymptotes at y equals 0. So let's begin graphing this. And I'm going to begin by plotting our ordered pairs and also by looking at our asymptotes. Now my ordered pairs are -2, 1, -2, 1, 0, 0, and then 2, 1. I also know that I have a vertical asymptote at -1 and at +1, and that I have a horizontal asymptote at y equals 0. Now let's look at the information that I was given about my first derivative. So my first derivative, I am told, is increasing on the interval from -infinity to -1, and then also from 0 to 1. And I'm told that I'm decreasing from -1 to 0, and that I'm decreasing also from 1 to infinity. For my second derivative, I'm told that I am concave up from -infinity to -1, that I am concave up again from -1 to 1, and that I'm concave up again from 1 to infinity. So if I look at each one of these sections individually, here I am increasing and concave up, which means that I look like the right side of the letter U. Decreasing and concave up means that I look like the left side of the letter U. Increasing and concave up, the right side of the letter U. Decreasing and concave up, the left side of the letter U. So let's put this all together with the points that I have in my graph. Now recall, a graph wants to get close to its asymptotes. So I know that to the left of -1, I should be increasing concave up. So I want to get close to my horizontal asymptote, go through my point, and then get close to my vertical asymptote, and I am increasing concave up. Then I am going to be decreasing and concave up. So decreasing and concave up. So I am decreasing, so still close to my asymptote, getting to my point, and decreasing and concave up. Then I'm told from 0 to 1, I am increasing and concave up. So I should be increasing and concave up. And finally, from 1 to infinity, I'm told that I am decreasing and concave up. So again, close to my asymptote, go through my point, decreasing and concave up. So this gray graph is the graph of f of x. Now the next few steps should look familiar. We've done this before. It says you can use the information from the first and second derivatives to graph a function. What do? You find the domain. We've done that before. You find x and y intercepts. You've done that before. This is the new part. Find any horizontal and vertical asymptotes at the function. Those are only going to happen when we have rational functions, like example 4. Then determine the intervals of increasing and decreasing using our first derivative. Determine concavity using our second derivative. Plot the points and sketch the graph. All of that is going to be the same. So we're going to find all that information so that we can sketch the graph of number 4. So example 4 is x minus 1 over x plus 1. So the first thing I want to do is find the domain. Well, what is the domain? Well, this guy here is a rational function. So in order to find the domain of the rational function, you set the denominator equal to 0. You solve for x. Any number you obtain that's real is a number that you exclude from the domain. So I'm going to say x such that x cannot equal -1, or if you wanted the interval notation for that, it would be -infinity to -1 union -1 to infinity. Either one of those is correct. X-intercepts, recall, in order to find the x-intercepts of a function, what we're going to do is set the function x minus 1 over x plus 1 equal to 0 and solve for x. Well, we can always put 0 over 1 and cross multiply. So 1 times x minus 1 is x minus 1, and 0 times x plus 1 is 0. So we end up with, adding 1 to both sides, x is equal to 1. So our x-intercept is 1, 0. Our y-intercept is always found by f of 0. So if we plug in 0 in place of our x, 0 minus 1 over 0 plus 1 is -1 over 1 or -1. So my y-intercept is 0, -1. Then we need to determine if we have horizontal or vertical asymptotes. Recall, to find a horizontal asymptote, you take the limit at infinity. So the limit as x goes to infinity of x minus 1 over x plus 1, well, this is going to be infinity over infinity, so we know we could use L'Hopital's rule. Well, L'Hopital's rule tells us take the derivative of the numerator. Well, the derivative of x minus 1 is 1, and the derivative of the denominator, well, the derivative of x plus 1 is 1, and then take the limit again. So the limit as x approaches infinity of 1 over 1 is just 1, which means that I have a horizontal asymptote at y equal 1. Vertical asymptotes, we try to factor and reduce. We'll recall our function is x minus 1 over x plus 1. I can't factor nor reduce that, so if I just set the denominator equal to 0 and solve for x, I get x is equal to -1. Therefore, I have a vertical asymptote at x equal -1. In order to find places where I'm increasing or decreasing, I'm going to need to find the first derivative. Well, this function, remember, is a quotient, so we're going to need to use the quotient rule. So f prime of x is going to equal the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. So if we were to clean this up, x plus 1 times 1 is just going to be x plus 1. Here, x minus 1 times a negative is -x plus 1 all over x plus 1 squared. Then we notice that our x's cancel and we just have 2 over x plus 1 squared. So the first derivative is 2 over x plus 1 squared. So then we have to figure out, where is this thing equal to 0? And where is it undefined? Because we need to find those critical numbers. We're going to move ourselves right up here. So where is f prime of x equal to 0? And where is f prime of x undefined? So in order to figure out where it's equal to 0, I just set the function 2 over x plus 1 squared equal to 0, and I solve for x. Again, you can put this over 1 and cross multiply, and you end up with 2 is equal to 0. Well, 2 does not equal 0, so that means that there's no x value where the first derivative is equal to 0. Is there any place where the first derivative is undefined? Yes, because it's a rational function, so we have to set the denominator, x plus 1 squared, equal to 0 and solve for x. Well, to solve this, I first take the square root of both sides. The squared and the squared cancel, and it's just left with x plus 1 is equal to 0, and I end up with x is equal to -1. So then on a number line, I write the number -1, and then I choose test values. To the left of -1, -2. To the right of -1, 0. So I need to figure out what is f prime of -2 and what is f prime of 0. Plugging into a calculator, remember this is our f prime. We get 2 divided by -2 plus 1 squared, and we end up with a positive number, which means that in this interval I am increasing. And then f prime of 0, again, 2 divided by 0 plus 1 squared, I end up with a positive number. So in this interval, I am increasing. So I'm increasing from negative infinity to negative 1, and from negative 1 to positive infinity. Where am I decreasing? Well, I'm not decreasing anywhere, so this would be none. And since I don't change from increasing to decreasing, we know that this would say no extrema, or none. So then I need to figure out where am I concave up or down, and what are my inflection points, and all of this depends on that second derivative. So let's start by finding the second derivative. Recall f prime of x is equal to 2 over x plus 1 squared. Well, if I want, I can rewrite this, because this is just a number, as f prime of x is equal to 2 times x plus 1 raised to the negative second power. Because since 2 is just a number, I can take what's in that denominator, make it a negative exponent, bring it up, and just use the chain rule. So the derivative here is going to be, well, f double prime of x is going to equal, well, 2 times negative 2 is negative 4 times x plus 1 raised to 1 less, which is negative 3, times the derivative of the inside, which is 1. So if I clean that up, the second derivative is negative 4 over x plus 1 cubed. And then again, I need to figure out where's the second derivative equal to 0, and where's the second derivative undefined. So to figure out where it's equal to 0, I set negative 4 over x plus 1 cubed equal to 0, and I solve for x. Well, for this, what I can always do is put my 0 over 1 and cross multiply. Negative 4 times 1 is negative 4. 0 times x plus 1 cubed is 0. Well, negative 4 doesn't equal 0, so there's no place where the second derivative is equal to 0. Where is it undefined? Well, it's a rational function, so I just need to set that denominator, x plus 1 cubed equal to 0, and solve for x. First, I take the cubed root of both sides to undo the cube, and I end up with x plus 1 is equal to 0. Solving for x, I get x is equal to negative 1. So then I grab my number line, and the only number that I put on my number line is negative 1. I choose my test values. From the left, I can choose negative 2. From the right, 0. And then I'm going to evaluate my second derivative at negative 2 and at 0. So grabbing a calculator, I have negative 4 over negative 2 plus 1 raised to the third power, and I end up with a positive number, which means that in this section I am concave up. And then I plug in a 0. Negative 4 divided by 0 plus 1 to the third, and I end up with a negative number, which means that in this interval I am concave down. So I'm going to be concave up from negative infinity to negative 1, and concave down from negative 1 to positive infinity. So then you're trying to find any inflection points, and you do know that you change concavity here. So you say, okay, well, I should have a point of inflection at negative 1 comma some value. So if I plug it into the original function, this x minus 1 over x plus 1, I would get negative 1 minus 1 divided by negative 1 plus 1, hit enter, and I get error, division by 0, because division by 0 is not defined. Well, remember that negative 1 is not in the domain of the original function, and since negative 1 is not in the domain of the original function, this can't be an inflection point, so my inflection points would be none, because again, negative 1 is not in the domain of the original function. So let's put all that together to graph our function. The difference from this and the other ones that we get is in this particular example, we have to find all our information, and in the other examples, our information is given at the beginning. So again, let's just make this graph and graph our function. So what we know is that we have an x-intercept at 1, 0, and we have a y-intercept at 0, negative 1. We also know that we have a horizontal asymptote at y equal 1 and a vertical asymptote at x equal negative 1. So here is our vertical asymptote at x equal negative 1 and our horizontal asymptote at y equal 1. We don't have local extrema or inflection points, and what our first derivative tells us, again, is that we are increasing from negative infinity to negative 1 and negative 1 to positive infinity. And what our second derivative tells us is that we go from being concave up to being concave down. So if we think about what that would look like, if we are increasing concave up, so again, increasing concave up looks like the right side of the U. And if we are increasing and concave down, we are going to look like the left side of the N. So here, next to negative 1, we know that we are going to be increasing concave up, and we know we want to get close to those asymptotes. So this is going to look like the graph from negative infinity to negative 1. And then we know that we are increasing concave down, so we are going to be increasing in concave down and going through our points. So this is the rest of the graph. That's it for section 4.4.